Every galaxy in the observable universe is supposed to have one. It's the invisible glue holding stars together, the reason spinning galaxies don't fly apart, the mysterious substance that outweighs every star, planet, and cloud of gas combined by roughly 6 to 1. Astronomers have never directly seen it, never touched it, never captured a single particle of it in any lab on Earth. But for 50 years, one thing has seemed almost universally true. Every galaxy has it, except apparently a small handful don't. In June 2026, a team of astronomers using the Keck Observatory atop a dormant volcano in Hawaii confirmed something remarkable. A faint, diffuse galaxy called DF9 appears to contain almost no dark matter at all. That alone would be strange enough. But DF9 isn't alone out there either. It sits on the exact same narrow, straight line in space as two other galaxies that share the exact same bizarre property, first discovered several years earlier. 3 galaxies, one suspiciously straight line. All 3 missing something every other galaxy in the universe seems to have. And the leading explanation isn't gentle. It involves an ancient, violent, high-speed collision between galaxies, one so extreme it may have physically torn ordinary matter away from dark matter itself, leaving behind exactly the kind of orphaned, dark matter-free objects astronomers are now finding, one at a time, strung out along a single cosmic scar in space. By the end of this video, you'll understand exactly how astronomers can tell a galaxy is missing something you can't even see, why this particular discovery matters so much for one of physics' biggest unsolved mysteries, and why finding a third example in exactly the predicted place is such a big deal. To be clear from the start, nobody involved in this research is claiming dark matter doesn't exist, or that this discovery somehow disproves it. If anything, these 3 strange galaxies may end up telling us more about how dark matter actually behaves than almost any other observation astronomers have made in years. Precisely because finding a place where it's genuinely, measurably absent gives scientists a rare natural experiment they can't get any other way. To understand why a missing substance matters this much, you have to go back to the 1970s, when astronomer Vera Rubin first provided solid observational evidence for something that would come to be called dark matter. Rubin was studying how fast stars orbit within spiral galaxies, and she found something that shouldn't have been possible if galaxies contained only the visible matter astronomers could actually see. Stars far out at the edges of galaxies were orbiting just as fast as stars closer to the center, which, under standard gravitational physics, should only happen if there's far more mass out there than what's visible. Extra material with enough gravitational pull to keep those outer stars from flying off into space. Rubin's measurements, and decades of follow-up evidence since, painted a consistent picture, something invisible, something that doesn't emit or reflect light in any way we can detect, is out there in enormous quantities, wrapped around galaxies in vast, roughly spherical halos. Based on everything astronomers have measured since, that invisible material, dark matter, is now estimated to account for about 85% of all the mass in the universe, not 85% of galaxies. 85% of everything, every star, every planet, every visible thing humans have ever observed makes up only a small fraction of the universe's total mass. For decades, one pattern held firm. Almost every galaxy studied, regardless of size, age, or location, showed clear signs of a dark matter halo wrapped around it, exactly as the theory predicted. That consistency is actually part of why dark matter, despite never being directly detected, remains the leading scientific explanation for what's holding galaxies together. The evidence, indirect as it is, has been remarkably consistent across an enormous number of galaxies. It's worth appreciating just how strange it would be, on its own terms, for something to break that pattern. Beyond Rubin's original rotation curve measurements, dark matter's existence has been supported by multiple completely independent lines of evidence over the decades, including gravitational lensing, where the light from distant galaxies gets visibly bent and distorted by the gravity of invisible mass sitting in front of them, and detailed measurements of the cosmic microwave background, the faint afterglow of the Big Bang itself, which encodes information about how much total matter existed in the early universe. All of these independent methods point toward roughly the same conclusion. There's far more mass out there than we can see, and it's distributed in a remarkably consistent way across nearly the entire observable universe. That's exactly why finding even one galaxy that seems to genuinely lack this invisible material was such a jolt to the field. Then, starting around 2018, astronomers found something that broke the pattern entirely. A team led by Yale astronomer Peter van Dokkum discovered a strange, diffuse galaxy called DF2, and its stars were moving far too slowly to hide any meaningful dark matter halo at all. It looked, essentially, like a galaxy made purely of ordinary visible matter, with none of the invisible extra mass every other galaxy seemed to require. It was such an unusual finding that some astronomers initially wondered whether the measurement itself might be flawed. Perhaps the galaxy's true distance had been miscalculated, which would throw off every other measurement derived from it. Or perhaps some subtle instrumental effect was producing a misleadingly low velocity reading. Van Dokkum's team spent considerable effort double-checking the distance measurement and ruling out these alternative explanations before publishing their conclusion with confidence. Then the same team found a second one nearby, called DF4, showing the exact same property. Two dark matter-deficient galaxies sitting relatively close to each other was enough to make astronomers take the possibility seriously. But it also raised an obvious question. Was this some kind of coincidence, a strange but isolated fluke, or was something deeper going on? That question is exactly what the 2026 discovery of a third such galaxy was designed to help answer. DF2 and DF4 don't just happen to sit near each other in the sky. When astronomers mapped their precise positions and velocities, they discovered something stranger still. Both galaxies, along with several other faint, low luminosity objects, fall along a single remarkably straight line. A linear relationship between where each galaxy sits in space and how fast it's moving. Astronomers call this a trail, and its existence strongly hints that all of these galaxies share a common origin, having been created or set into motion by the same ancient event, rather than forming independently and coincidentally lining up by chance. If that idea is correct, it makes a very specific, testable prediction. Any other galaxy sitting along that same trail should also turn out to be missing its dark matter, because it would have formed through the exact same process as DF2 and DF4. That's precisely the prediction a Yale-led team, headed by PhD candidate Michael Keem, set out to test in 2026, focusing on a faint galaxy on that trail called NGC 1052 DF9, or DF9 for short, chosen specifically because, among the untested galaxies on the trail, it most closely resembled DF2 and DF4 in size and brightness. DF9 sits in the NGC 1052 galaxy field, roughly 65 to 67 million light-years from Earth, in the constellation Cetus. To measure whether it truly lacked dark matter, Keem's team needed an instrument sensitive enough to track the incredibly subtle motion of individual stars within a galaxy this faint and this far away, motion measured in mere kilometers per second, detected purely through tiny shifts in the wavelength of starlight. They used the Keck Cosmic Web Imager, known as KCWI, a specialized instrument mounted on the Keck 2 telescope on Mauna Kea, specifically designed to study faint, diffuse light sources that ordinary telescopes struggle to resolve in detail. KCWI works as what's called an integral field spectrograph. Rather than capturing a single, simple image the way a normal camera would, it captures a full spectrum of light for every individual point across the galaxy, simultaneously, effectively building a three-dimensional dataset that combines an image's spatial detail with the detailed wavelength information normally only available from a single-point spectrum. That combination is exactly what makes it possible to measure the incredibly subtle, star-by-star motion inside a galaxy this faint, rather than only capturing its overall brightness and shape. Over 2 separate nights, the team collected nearly 11 hours of exposure time, split between observing DF9 itself and observing nearby patches of empty sky, used afterward to carefully subtract out the faint background glow of Earth's own atmosphere from the final measurement. That's an enormous amount of dedicated telescope time for a single, faint dwarf galaxy, a reflection of just how difficult it is to extract a reliable signal from an object this dim, sitting tens of millions of light-years away. Here's the actual physics behind why this measurement works at all. Stars inside any galaxy orbit at a speed determined by everything gravitationally pulling on them, the combined mass of every visible star, every cloud of gas and dust, and any invisible dark matter halo wrapped around the whole system. Pack in a massive, unseen halo, and the stars whip around fast, resisting the pull of gravity by moving at higher velocities. Take that invisible halo away entirely. The same stars drift far more slowly, held together only by the gravity of the visible matter they can actually see. The result Keem's team found, DF9 stars showed a velocity dispersion of just 5 kilometers per second. For comparison, if DF9 contained a typical expected amount of dark matter for a galaxy of its visible size, astronomers calculate its stars should be moving at roughly 24 kilometers per second, nearly 4 times faster than what was actually measured. That gap isn't a rounding error or a measurement quirk within normal uncertainty. It's a massive, unmistakable shortfall. The team calculated DF9's total mass at somewhere between roughly 100 and 140 million times the mass of our Sun, a number consistent entirely with what its visible stars alone could account for, with essentially no extra mass left over to explain as an invisible halo. A typical galaxy with this same amount of visible stellar mass would be expected to weigh roughly 100 times more once its dark matter halo is factored in. DF9 simply doesn't have that extra weight. As Michael Keem put it in the Keck Observatory's own announcement, The instrument's exceptional precision made it possible to measure DF9's extraordinarily low mass accurately enough to actually demonstrate the galaxy's lack of dark matter, rather than leaving the result ambiguous. Finding one strange dark matter deficient galaxy could plausibly be dismissed as an unusual fluke or a measurement error. Finding two nearby ones raised eyebrows but still left room for coincidence. Finding a third, specifically along the same predicted linear trail, exactly where a particular theory said it should be, is a very different kind of evidence entirely. The leading explanation for how DF2, DF4, and now DF9 could have formed is something astronomers call a bullet dwarf collision, a concept first proposed for DF2 alone back in 2019 by physicist Joseph Silk. The idea works like this. When two dwarf galaxies collide with each other at extremely high speed, their respective clouds of gas can slam into one another and become physically disrupted, shocked, and compressed, while each galaxy's invisible dark matter halo, which barely interacts with anything except through gravity, largely passes straight through the collision undisturbed like a ghost moving through a wall. If conditions are right, the compressed, shock-heated gas from the collision can end up flung outward, separated from the dark matter halos that used to surround it, and can then cool and collapse under its own gravity to form brand new galaxies made almost entirely of ordinary matter, with little to no dark matter along for the ride. This isn't just an abstract idea. Astronomers have directly observed something similar happening on a much larger, more dramatic scale in an object known as the Bullet Cluster, where two enormous galaxy clusters collided, and follow-up observations clearly showed the hot gas from the collision separated from the location of the dark matter, exactly as gravitational lensing measurements would predict if dark matter really does interact only through gravity and nothing else. The Bullet Cluster has been described by many astronomers as some of the strongest direct evidence supporting dark matter's existence in the first place, precisely because the separation between the visible gas and the inferred dark matter location was so clean and so clearly visible in the data. The bullet dwarf hypothesis proposes something conceptually similar, just at a much smaller scale, involving individual dwarf galaxies instead of massive clusters, hence the name, a smaller scale echo of the same basic physical process. It's worth pointing out just how specific and risky this kind of prediction actually was when Silk first proposed it in 2019. At the time, DF2 was still a single unusual data point, and proposing an entire physical mechanism to explain it, based on just one example, was a significant scientific gamble. The kind of idea that could easily have been quietly forgotten if no further evidence ever turned up to support it. The fact that DF4 turned up soon after, sharing the same trail and the same missing dark matter, was the first sign the idea might have real legs. DF9's confirmation in 2026, specifically targeted because the trail theory predicted it should behave this way, represents the strongest test of that original 2019 proposal yet. If DF2, DF4, and DF9 really did all form together this way, from gas stripped away during one single ancient, violent collision, it would explain both of the strangest things about them at once. Why each individual galaxy is missing its dark matter and why all of them happen to sit along the exact same straight line in space, moving at velocities that trace back to a shared point of origin. DF9 becomes what scientists call a genuine test of that prediction. A case where the theory said, look here, and you should find another dark matter deficient galaxy. And when astronomers actually looked, that's exactly what they found. As Kame described it in the Keck Observatory's announcement, the three galaxies together now look like extraordinary exceptions that likely formed together in one violent event that physically separated ordinary matter from dark matter. That combination, a specific falsifiable prediction followed by a targeted observation that confirmed it, is exactly the kind of evidence that moves an idea from interesting speculation toward genuinely well-supported scientific explanation. It doesn't prove the bullet dwarf collision theory beyond all doubt, but it's a meaningfully stronger form of evidence than simply noticing two unusual galaxies happen to look similar. It's worth being precise here, because the headline finding, as striking as it is, rests on a measurement sitting near the very limit of what even a powerful telescope like Keck can currently detect. That velocity dispersion measurement of 6. 5 kilometers per second carries real uncertainty. The published research places the range at roughly +3, 9, or -4. 3 kilometers per second, meaning the true value could plausibly sit anywhere from around 2 to 10 kilometers per second, given the limits of current measurement precision. That's a wide enough range that some caution is appropriate before treating the number as an exact final measurement. Even so, every value within that entire uncertainty range still sits dramatically below the roughly 24 kilometers per second astronomers would expect if DF9 had a typical dark matter halo, meaning even the most generous interpretation of the uncertainty still points toward the same basic conclusion. DF9 is missing the dark matter a normal galaxy its size should have. The research team has also been careful to note that DF9 wouldn't have been considered a target worth this level of scrutiny at all if the bullet dwarf collision theory hadn't specifically predicted it should be unusual. This wasn't a random galaxy that happened to get measured and turned out to be strange. It was chosen deliberately because the theory said to look there, which is itself worth keeping in mind when evaluating how strong the confirmation really is. A successful, specific prediction carries more weight than simply finding an anomaly by accident, but it also means the result is, by design, exactly what researchers were hoping to find, which is worth acknowledging honestly rather than treating the outcome as an unbiased surprise. There's also more work ahead before this story is fully settled. The research team has said that future observations, using both existing telescopes and upcoming instruments, will aim to search for any leftover gas that might still be drifting near these galaxies from the original collision. Gas that, if found in the right location and with the right properties, would serve as even stronger, more direct evidence for the bullet dwarf scenario. Researchers also want to better constrain exactly how much ordinary gas each of these three galaxies contains today, which would help pin down their total mass even more precisely, and could potentially help distinguish between slightly different models of how dark matter behaves under these extreme violent conditions. So this is genuinely strong, carefully gathered evidence pointing in one specific direction. But it's not the absolute final word on the subject, and the scientists doing this work have been transparent about exactly where the remaining uncertainty lies. There's a broader lesson here about how this kind of frontier astronomy actually works, which makes the story more interesting rather than less. Measuring anything about a galaxy this faint, this far away, pushes right up against the physical limits of what even the world's most advanced ground-based telescopes can currently achieve. Every step of the process, collecting nearly 11 hours of exposure across 2 separate nights, carefully subtracting atmospheric glow, modeling the uncertainty in the velocity measurement, cross-checking the result against the specific numerical prediction the collision theory made in advance, represents astronomers working right at the edge of their instrument's capability, and being honest, in the published research itself, about exactly how confident that leaves them. That's not a weakness in the discovery. It's actually a sign of good science. Rather than rounding a difficult borderline measurement into a falsely confident headline, the research team published their actual uncertainty range, alongside their central result, letting other scientists evaluate the strength of the evidence for themselves. So here's where this stands right now. 3 galaxies, DF2, DF4, and now DF9, all sit along the exact same narrow linear trail of faint objects in the NGC 1052 field, and all 3 show the same extraordinary property. Almost none of the invisible dark matter that seems to dominate nearly every other galaxy in the observable universe. The leading explanation is a violent ancient collision between dwarf galaxies, one energetic enough to have physically ripped ordinary matter away from its dark matter halo, leaving behind exactly this kind of dark matter orphaned trail of objects. DF9's discovery specifically confirmed a prediction the collision theory made in advance, which is a genuinely strong form of scientific evidence. But the measurement itself sits close to the edge of what current instruments can precisely detect, and researchers are still working to gather more direct evidence, like leftover gas from the original collision, before the story is considered fully closed. The bigger question this raises goes well beyond just these 3 faint, obscure galaxies. If ordinary matter really can be separated from dark matter under the right violent conditions, it tells physicists something important about how dark matter actually behaves, that it responds differently to violent collisions than ordinary gas and dust does, exactly the kind of behavior theoretical models of dark matter have long predicted, but rarely had this kind of direct, testable evidence for. Every galaxy, like DF9, that gets confirmed adds one more data point to one of the most important open questions in modern physics: what dark matter actually is, and how it behaves under conditions extreme enough to tear the universe's ordinary building blocks apart from whatever else makes up 85% of everything that exists. There's also a genuinely exciting next step already being planned. The same trail of faint galaxies that contains DF2, DF4, and DF9 almost certainly contains other members that haven't been measured yet, meaning astronomers already know roughly where to look for a 4th, or even 5th, dark matter deficient galaxy if the collision theory continues to hold up. Each additional confirmation makes the case stronger, the same way DF9 strengthened it beyond just DF2 and DF4 alone. It's rare in astronomy to have a theory make this specific a prediction, and rarer still to be able to go out and test it again and again, one faint galaxy at a time, along the exact same cosmic scar in the sky. If you want to be here when astronomers find the 4th galaxy on this trail, or when new observations finally locate the leftover gas from the original collision, subscribe to the channel and turn on notifications, because the moment new findings come out, we'll break them down here with the real data, not the invented version. 3 galaxies, 1 straight line, a collision written into the sky. Whatever the next observation reveals, Whether it's leftover gas from the original collision or a fourth galaxy joining this strange trail, this is one of the rare places in astronomy where a specific theoretical prediction is being tested, one faint galaxy at a time in real time, right now. Thanks for watching.